Let me share my screen. So where is it? Is this okay? Right. So okay, let's begin. So good evening from Singapore. It's 1:30 a.m. over here. So I'm PK. I'm from the Center for Quantum Technologies, National University of Singapore. So for us, we are a quantum computing group or quantum optics. So what we are going to share with you today is temporal intensity interferometry. Some of you may know this as G2 or the Hamburg-Brown twist effect. But our approach, or rather our original intent, was not SETI. We are approaching this from a basic science kind of viewpoint. So just got to share with this for your consideration. So let us begin with a question. So the question we ask is, if this is a measurement that you see as an observer without any a priori information of the source, what would you think? Well, perhaps you think that the continuous spectrum might be some form of black body radiation, a star possibly, G-type, 6,000 Kelvin, around there possibly. But what about that narrowband emission? Would you think that it's a natural emission, an atomic emission line, a laser line? What information do you need to make such a conclusion? Is it because the spectral width is narrower than, say, Doppler broadening? Is it because it has some timing modulation in it, some form of pulsing? Those two, I think, are convenient and I think very useful markers. But from a basic science viewpoint, both of these are not required or intrinsic qualities of laser light. Because what is laser light when it boils down to it? We approach this question from the viewpoint of photon statistics. And I think this has some overlap with something Paul Horowitz briefly mentioned just now on the Mach-Zehnder interferometry or higher correlations of light. In this case, we are considering the second order correlation of light. So what we are looking at is the timing distribution of the photons themselves. There are three scenarios that we can consider. So from left to right, left is coherent light. So in this case, the photons will obey Poissonian timing distribution. In this case, this will correspond in practice to laser light, and actually only laser light. In the middle, anti-bunching. This corresponds in practice to a single photon source, such as quantum dots. And on the right, photon bunching. This is when the photons have a tendency to propagate closer together than the random Poissonian statistics. So photon bunching will correspond to thermal light or all-star light, as you know. So how do we measure this? Is we perform a G2 measurement, and a G2 measurement is essentially a correlation measurement between the photons as a function of their timing separation. So from left to right, if it's a coherent laser light, well, the G2 will be flat because it's a random distribution. There are no bias or preference to any timing separation, and therefore a flat, unbiased G2 signature. The one that we're interested is also on the right, which is photon bunching, which will correspond to thermal light or starlight. Therefore, in the situation or scenario for optical SETI, we present the question for your consideration. If a entity or someone is to generate an artificial laser light, well, that light would be the one on the left, coherent G2, G2 equals 1. But that light would probably be embedded in the starlight of its whole star, and that would be a G2 photon bunching on the right. Is it possible then to differentiate or identify the presence of such a laser light, regardless of its line width, regardless of its timing modulation, whether it's continuous or pulse? Can we identify its presence? So this is still theoretical. Can it actually happen? So how do we measure this? Basically, in an oversimplified manner, from left to right, you start with a light source, you impinge it on a beam splitter, split into two photon detectors, and you measure a timing correlation between these two events. Essentially, a two photon coincidence events, if you will. And an oversimplification, if it's thermal light, you expect a bunching signal. And if it's a coherent laser light, it will be flat. So these two are the extreme cases, if you will. So instrumentation setup, let us do a simulation setup in the lab just as a sanity check. So in the top half of this diagram is the light source. On the left, we have a laser diode, and slightly on the right, an argon arc lamp. So the argon arc lamp has an effective temperature of about 6,000 Kelvin. So this produces the black body radiation that actually you saw earlier. So by combining these two light sources, you see a continuous spectrum with one narrow emission line. This will be our test case. So the instrumentation on the bottom is what we are going to use to see, can we tell a difference? Can we identify the presence of a laser light at all? So roughly from left to right of the bottom diagram, the grating monochromator in this case is some form of it's essentially a bandpass filter. We then pass through Fabry-Perot etherons, which are kind of a narrow band optical filters. So effectively, we reduce the overall black body radiation of what, a few hundred nanometers. We reduce the spectral passband by 5 orders of magnitude to picometer bandwidth. And then we perform a G2 timing coincidence with a window of 40 picoseconds. The reason for filtering down is to increase the coherence time of this bunching signature to about nanoseconds so that our detectors with that 40 picoseconds can resolve in the first place. This will allow us to differentiate between a bunching thermal light and a flat coherent G2. So do we have the data to show? So oversimplified version of our expectation. So if we begin with a continuous black body and one narrowband emission line, there are two situations. If the narrowband emission is thermal and if it's a coherent laser light. So let's begin with, what if the emission line is a thermal line? Well, we simulate this by having the laser light pass through a suspension of microspheres. This causes a phase randomization of the light, which causes it to have zero-thermal properties. So essentially what we have is a zero-thermal narrowband line embedded in this broadband black body radiator. The G2 we observe is this. We see two photon bunching signature. The one that we label as B, the smaller signature, corresponds to the black body component because that is nanosecond coherence time due to the epsilon. The spectral filtering constrains the black body light to this bunching coherence time. In contrast, the narrowband emission line from the zero-thermal laser, because it's narrower than the epsilon, the inverse of it, the coherence time, is wider. And in this case, it's about 20 megahertz. So if the line is pseudo-thermal or thermal, we can actually extract two information. One, it is not a coherent light source. Two, we can actually extract some information of its line width. So now the interesting question is, what if it is a coherent laser light? What should we see? So we change the light source, we remove the suspension and just have a coherent laser light. And we will see this. If we block the laser light, just the black body component, we see this photon bunching signature in red. Expected is just the bunching signature. If we introduce thousands or tens of thousands of laser photons per second, it reduces the overall bunching signature. And if the spectral density of the laser light and the thermal contribution is comparable, well, it basically suppresses the black body component and it flattens out. This, I think, is a smoking gun because there are no other ways that a single spatial mode, well-defined narrowband light can have a flat G2 equals 1. The only way to do so is a coherent laser source. And if we think about it, a natural laser source will probably not have mirrors and cavities to constrain the spatial mode. So the only way to have a spatially coherent laser light will require some artificial intervention to build a well-defined resonator and all those things. So that, I think, might be of some interest. That being said, I think this will be extremely difficult to implement in the astronomy. But let's give it a try. So we push it a bit. Can this work outside of the lab? So as a reminder, rate this bunching signature if it's thermal. That's what we are hoping to see. Can we see it from the only star we can see in Singapore, which is the sun? Turns out we can. And even though Singapore has like 100% humidity, tropical clouds, monsoon rain, haze from Indonesia, and all those jazz, we can see this signature relatively easy. There are no observatories in Singapore. This was measured outside my office window, like random day. And we can consistently see this any time of the day. So this gives us some confidence that a G2 measurement is very robust and does not require the sensitivity of a Michelson interferometry. So this was also one of the thoughts we have, that maybe we can make do with this without adaptive optics or very nice mirrors. Maybe a CTA 12-meter scope might have a chance to actually use this, maybe. So the next question we have is, other than the sun, can this work on, say, any other star? Because maybe that would be interesting. So we accessed the nickel telescope courtesy of Andrew a couple of times during 2019. So we made our setup slightly small, such I can squeeze it into a luggage and pass the US customs. We went up Mount Hamilton and we just put it there. It did not immediately work because this is my first time seeing a telescope actually. So there were issues, optical stability, mechanical stability, temperature fluctuations. But we learned from our mistakes. We spent over 6 nights measuring. So we came back to Singapore. We rebuilt a second prototype, some mounting brackets for the nickel, internal, some optics, just to give you a sense. So some of the mirror mounts, folding mirrors for the degrees of freedom of control, tilt stage, add-on holders for the spectral filtering, bandpass filter. Well, won't bore you with the details at this point. The interesting part is this is a drawing. This is the real thing. We have already finished it and we were ready to fly. Last year, January, we booked timing with the lead observatory, and until United Airlines canceled us and COVID-19 happened. So this is now sitting in the lab, and we hope one day we can fly over and see something interesting. So till then, this is the state of progress for temporal intensity interferometry. Hope it is slightly interesting for some of you, either directly or maybe someday in the future. I don't know. With that, I thank you for your attention. Thank you.
Thank you, PK. I see Paul has a question.
Yeah, so a couple of questions for you. Sure. One is that if you're going to measure correlations with fast paired beam split detectors, then you're limited to optical bandwidths, which are of order the inverse of the resolving time, which requires extremely narrow spectral. You have to know exactly the wavelength of what you're looking for. And
yeah, that I agree. That is a problem. So for the purpose of SETI, I would imagine that this technique will only be useful as a follow-up. So I would think that maybe some form method like the pulsing or maybe panel SETI, maybe those kind that you have all sky or the time measurements would be good for the first measurement. When you have candidates, this can act as a follow-up to verify, is it some form of thermal line or is it a coherent line? I think that may be interesting. Yeah.
Okay, but then I guess the second half of my question is, you have your little cell with particles in it to randomize the phases. And of course, the atmosphere tends to do that also through atmospheric scintillation. Have you thought about of course, the sun, there's no problem because it's already random, but in the case of a laser, what about the atmosphere?
I agree, we should test that, whether the fluctuations for atmosphere will actually cause the laser light to be zero thermal. I agree.
Yeah, thanks. So Jamie also mentioned that Veritas is doing intensity interferometry. So just for so for CTA, this is also something that we can also measure with scintillation. So there have been some ideas about scintillation testing. So that is something we can collaborate on.